Okay, good evening, everyone, once again. So this is a new week, and last week we did a lot of mathematics, calculus with linear regression, basically manually doing it and then doing it with a stochastic gradient descent and then writing some code to do that. And the whole idea was for us to get a very good grasp of, the mechanisms behind all of the regression and all of that, all of those things that we do, right? Because at some point very soon, we will be switching to where we will kind of transfer that to machines, what I mean by machines, libraries, the libraries like sklearn, scikit-learn, libraries like, PyTorch, TensorFlow. Those are the libraries that will be helping us to do a lot of this mathematics so that we won't have to do it ourselves. But I would prefer that we at least get a feel for it and have a good understanding of what's going on under the hood before we jump to just doing it with the libraries. So today we will do a bit more of hands-on. Last week we had done the linear regression with single variable using gradient descent. And then I did a little bit of intro on linear regression with multiple variables, again, using gradient descent. So I'm going to go through that today, kind of formal formulation of that process. Then I'm going to do a bit of hands-on so that everyone can understand all of the principles behind it. So when we say multivariable linear regression, it's the same thing as a single variable linear regression. It's a statistical method, but this time we're using two or more independent variables. So not just an x, y equals mx plus c, which is a single variable, a single independent variable, and a single dependent variable being y. We also now have y equals m1x1 plus m2x2 plus m3x3 and so on plus c. So we now have multiple independent variables, the x1, x2, x3, and so on. In this screen here, you see a formulation. We are using beta rather than rather than m. It's essentially the same thing, right? So you have all of this beta 1 x1 plus beta 2 x2 all the way to beta n xn. Then we have beta 0, which we now take as a c, which is the constant or the intercept on a linear graph. And then there is this other thing here, which I won't talk about a lot, but it's epsilon. It's essentially a term that we use to correct for errors, what we may call numerical errors or random variations in our model or in the toolkit or whatever we're using to calculate it. So typically, we don't worry too much about this because the value of epsilon is really very small in most cases. So that's what it is. So you essentially extend that principle that we applied for a single variable, except that now we will be doing it on multiple variables. Now, so doing that, right, requires for you to be able to calculate a cost function, right, that is dependent on all of the independent variables, right? Just like you did a single cost function. So you're going to have a cost function that is dependent on a lot of the, all of the independent variables. And then you are going to have to calculate the gradient of each of those parameters, for each of the independent variables, each of the coefficients for each of the independent variables. You calculate that, how the value of the cost function changes when you change the independent variable coefficient. So basically, for each parameter, you calculate the gradient. So it's the same thing. And I'm going to show you how you would transform that principle. The same thing that you are applying, in a single variable, you will now do it for multiple variables. So that's basically, the multivariable linear regression. And essentially, in the real world, most of your models will have multiple variables. Consider each variable, each independent variable as an input or a feature that contributes, to the thing you want to model, the system you want to model. And then the Y being the output. In fact, in the real world, you have multiple Ys as well, but we're not going to go into that yet. Maybe we'll talk about that when we go into more, complex systems, and we don't have to be thinking about the maths of it. So here you see that Y is a dependent or predicted variable. The beta 0 or C, if you look at what we were doing before, that is the intercept, the Y-intercept, or what we call a constant value, which is the value when all the X variables are 0. That would be the value of Y. And then you have the beta 1, beta 2 to beta n, which you could also call M1, M2, Mn, if we go by the other notation. Those are the coefficients or slopes of each independent variable. That represents the change in Y for one unit change in X, right? Then, of course, the X1, X2 to Xn, which forms the actual independent variables. So those are the elements that will make up a multivariable linear regression. Then, of course, we have the epsilon, but I'm not going to bring this into what we are doing for now, just to minimize the complexity of what we're trying to do. Okay. So now a typical problem set is usually, this is now kind of, I'm going to switch into showing you how to do this before I come back to the matrix, because the matrix notation brings in a lot of this mathematical notation, which again will throw a lot of people into a whole bunch of confusion. So I want to take this step by step. It's not really difficult, right? It's just in mathematical notations and make it look like it is difficult. So I'm really just going to make this very, very simple, right? So let's go to our Jupyter Notebook and I can show you how this works. So the first thing, I'm going to create a new Colab, Jupyter Notebook in Colab. And then I'm going to start off with doing the simple thing that we did before, which was linear regression with a single variable. That linear regression with a single variable, I will then extend it to 2 variables. So typically, if you are doing linear regression with a single variable, right? What you would do, so let's assume we have some numbers. So let me go get some numbers. I have some numbers here, which looks like the assignment. So I don't want to rehash what we had in the assignment. Rather, I'll generate a new set of numbers. So here's a new set of numbers. Now, the first thing I want everyone to pick up is we can use NumPy. NumPy will make things easier. So we don't have to be looping through each element, when we are doing the maths, okay? You can just multiply the entire, lists or the entire array, using NumPy. So we will import NumPy. as NP, right? We'll also import matplotlib. So we just want to keep that in there. The first thing you have to do is this is your X values, the first one. So your X values, we will make it a NumPy array. So np.array. It's as simple as that. And then, put this whole thing in there. Then your Y, which is the value, the actual values that we want to predict, you put it in there. So you have imported NumPy. I'm going to run that. And then you have initialized your array. The steps for linear regression are very simple. The first one is, okay, so yeah, I need to put in the commas. So I'm going to have to put in the commas. I just picked this from somewhere. It wasn't well formatted, but yeah, we will do this ourselves now. So I hope these numbers, it's easy to understand these numbers. These are just floating point numbers, no big deal. There's nothing special about them. Numbers, decimal numbers with a lot of decimals in them, right? So right. So we have the X's all set up now, the Y's. Okay. So yeah, so this is now who I can now print X and Y, and we will see the values. These are NumPy arrays, and you can see values here. So the first step in a linear regression is calculate the predictions, right? You can use a function to do that. But in this case, because it is a very simple linear equation, we don't really need to put it in a function. In the previous examples, I used to put in a function because I kind of wanted to establish mentally the process. But yeah, so you can do that, okay? Define y spread, okay, of x. And so now they're using theta, but I'm not going to use theta. I'm going to just use M and C for now, M and C, which are the parameters. So you just return X times M. So Y equals MX plus C. So that is our prediction. You really don't need to do this function. You could actually just do it, as individual steps. But I like to do this because it begins to establish a process in our heads. It makes the code a bit more verbose, but yeah. So the first step is that. The second thing is you should be able to calculate the error. So calculate the cost. So now, in previous times, I've been interchangeably using the terms cost function and loss function. And it sounded like they were not different, or they were more or less the same thing, but they're not exactly the same thing, right? The cost function, the loss function calculates the error of a single data point, while the cost function calculates the error of the entire set of data points. That's the difference. So a cost function for MSE would be the square error. That is the y minus y hat for a single data point. But the cost function is the summation of the squares of y minus y hat divided by n. That's the average. That's MSE. So we have to be, sometimes it's easy to interchange it too. So that's the difference. And I think you can go do some checks. Right. So the cost function, to now get the value of the cost function, it's basically y minus the predicted value, right? The actual value minus predicted value. It could also be the opposite. So NP dot mean is actually the mean, not the sum. Okay. So and it's pretty easy to do it that way, right? So NP dot mean, which is the average value. The average value of y minus the predicted y, which is mx plus c. You can actually see that I don't really need to do this here. I can just do m times x plus c. And that gives me the same thing. That gives me the same thing. And then multiply by 2. You would probably need to put this in brackets to be sure that you have the right order of operations. But yeah, either way, it's the same thing, right? So this gives you the cost function, which is the error. Okay. Now, the next thing is to calculate the gradient. So this is where I had a bunch of people that were saying they did not understand the maths behind it. So I'm going to do a little bit of the maths behind it, right? So let's look at that. Let me use my Excalibur, pad and see if I can explain the maths behind it. So the idea is this. If you remember the equation, for cost function based on linear regression, the mean square error. So based on the mean square error, we'll remember that the mean square error, MSE, is 1 over n. That is what gives you the average summation from I starting from 0 and going all the way to n, right? Y minus y hat, okay, squared. That is the mean square error. Now the gradient, which is the mean square error, which is also the cost function j. So j is well, in general machine learning terms, we call it j theta. I'll talk about that later on. J is a general term or letter we use to represent a cost function. The theta is a matrix version of all the parameters. When you take all the parameters and you put it in a single, you convert it to a single matrix, it's called theta, right? So now, yeah, mean square error is also j. So if I want to do the derivative of j, which is the mean square error in this case, with respect to m, right? What we are going to do, if you remember, is the 1 over n is a constant, so you bring it out. Then remember the derivative, you have a chain rule. The chain rule that says that dy dx, right, of any function of x, right, is equal to, sorry, I didn't write that properly. Dy dx, so let me write this. So let's do this, right? Our calculus tells us that if you have a function y equals to f of x, right, then dy dx is going to be something like this. Dy dx, this is just not a partial derivative, but it's going to be f prime of x, right? Which, if x is a composite function, then if it is a function of x, then we use a chain rule where we said if dy dx is uv, then dy dx is u dv dx times v du dx. Sorry, u dv dx plus v du dx, and all of that stuff. I don't really want to go into all of that. But when you kind of bring it down, it's going to be something like this. If the function, this is where it's written, like if you have g of f of x, right? In other words, the y is a function of another function of x, then you can simplify it by just doing you do dg dx. Now it's getting more complicated, and then you multiply it by the f dx, a chain rule kind of, right? Because f of x, or yeah. So this is kind of let me bring this down again. So if you had a function like y equals let's use an example. We have a x minus 2 all squared, okay, which is basically a g of f of x, right? In this case, you would say that the g equals, let's say, a squared, right? And the a is x minus 2. So you have two functions. That's basically g of f of x. So the derivative of the of y would be 2a times the derivative of a with respect to x, okay, which is going to be 2a. And if you do the derivative of a with respect to x, that's just this one here, you are going to get just 1. So it's 2a times 1. So effectively, all of this just becomes 2a times 1. Now, what if we had 2 here? Then it would be 2x minus 2 all squared, right? So a is 2x minus 2 in this case. So it will be 2a times the 8x. And what you have, I didn't write this properly, but I think I will rewrite it if we need the summary. So this will now be 2a times 2. So why is it 2a times 2? Because the law of differential says the a, the dy, the a. So this is what it is. If y is g of f of x, right, then dy dx will be dy dg times dg dx, which, you know, it breaks it down. And you could even go further and just chain it, the GDF times the FX. You can just keep chaining it that way. That's a chain rule, right? So, but I'm going to take this off to avoid confusion. So anyway, I'll quickly get past this point. So for our specific case, right, where we are now doing this for the you know, for this function, if you look at it again carefully, you will see that this function Okay, 1 second. So you will see that J is, let's start off by spreading this out. So the summation doesn't really matter because, by the way, I forgot to mention this should be yi, this should be y hat I. So it's y. So basically, this is like saying y1 minus y hat, y1 hat, or y hat 1 squared, right? Plus y2 minus y hat 2 squared plus no y3 minus y hat 3 squared. And basically you just keep on going all the way to plus yn minus y hat n squared. So you are doing differential of functions, right? So what that means effectively is that because you are doing it for different functions, you can do it for one as well. You can do it for one at a time, basically. So oh yeah, I was actually looking for a way to do this. So you can do this for each one separately. Okay, so having a bit of difficulty with this. So what this means is when we are doing the derivative, we can do it one by one because the derivative of a sum of numbers is the same as the sum of the derivative of those numbers. This is a basic principle in integration and differentiation. Same thing with integral. The integral of a sum of numbers is exactly the same as the sum of the integral of each of them, right? Yes, that is a basic rule. So that means I can do derivative of each of them separately. So if I do the derivative of this, I'm going to get if I do the derivative of this, right, what I'm going to get is 2, right? Because you bring the 2 back, it is 2 minus 1, 2 times this, 2 minus 1. That's basically that. So I'm going to get the 2, and then I'm going to get y1 minus y hat, right? y1 hat. The square sign goes, but we will now have to do a, we have to do the ddx or x, yes, ddxi, because you are doing for each of them ddxi, sorry, not ddxi, the coefficient of, because remember you are doing with respect to m. So for each m, you have to do it for each m, right? I forgot to mention this. So you have to do it for each m. So we are taking one m. Remember the m is in here. I can expand this. If I expand this, right? Remember this is mx plus c. So it is m1x1 plus c, right? Plus c1. In this case, the ones refer to each data point. So if I do that, what I will have ddm1, because we are still doing respect to m1, of m1x1 plus c1. Everything is 1, right? This is not looking very good. So plus c1. That will lead us to this, which is 2 times yi or y1, no, minus y1 hat, which you already have. If you do this whole integral, because you are doing respect to m or m1, we will have x1 here as a value. C1 is 0, so it's basically x1 plus 0. So this is your derivative. Okay, that's your derivative. If you do the same thing for all of them, you will end up with a similar outcome, where for each of them, you are going to have 2y2 minus y hat 2 times x2. And then you will have 2 again into y3 minus y hat 3 times x3. And that keeps going until you have 2 into yn minus y hat n times xn. So all of this will easily go into a single summation. When you do that summation, right, you do that single summation, you're going to have this. You're going to have summation 2 into yi minus y at I times xi for every I that starts from 0 to n. And I forgot that when you do this summation, remember you are doing this summation and you are actually taking an average. You're taking an average, that's why you have, that's why you have 1 over n here. So your 1 over n is still going to apply here. So at the end of the day, you're going to have 1 over n. So this is going to basically, if you sum any number times this, it's basically like saying 2a plus 2b plus 2c plus 2d and so on to 2n. You can take all 2xa. In fact, let's do it 2ax plus 2bx plus 2cx plus 2dx plus all the way to 2nx. You can factorize out the 2 and the x because they are common to all the terms. And then you have a plus b plus c plus all the way plus d all the way to plus n. And this is basically what happens here. So when we do that here, what we will get is pulling the 2 and the x out of the summation, just like we kind of, factorized it out here. Okay. Just like we factorized it out here. So here we will also be able to factorize it out, and we will have the 2 and the x goes out. So you have 2x. No, the x doesn't go out because the x is dependent. The x follows with the data point, but the 2 is constant. So we will take the 2 out, but will not take the x out. So it will be 2 over n, right, times summation xi, okay, into yi minus y hat I, right? That is a cost function. That's rather the gradient. This is the gradient cost function. The interesting thing is that in some formulations of this, you see a minus here. And the reason why it's minus is if I did, okay, sorry, I think here it should be a minus because I made a mistake. There is a missing piece here. I forgot that the y hat itself is minus. There's a negative sign. So this function is actually negative of mx plus c. So that's the piece I missed. This function is negative of mx plus c. So because it's negative of mx plus c, this x is going to be a negative x. So that affects the two. So all of this is minus basically. And so you end up with a minus down here. You end up with a minus down here, and that minus goes down here. So at the end of the day, you are going to have something that looks like minus 2 over n times the sum of each x for each data point times the error between the actual y in that data point and the predicted y in that data point. That's how we derive the gradient. And this is all just for mean square error. We spent 30 minutes on this. So I hope that has satisfied those who were trying to understand a bit of that calculus. All right, so let's move on. So the gradient for x, y, mc is still going to be the same thing. Now here we are calculating the gradient of the m. Oh, by the way, I forgot for the c, it's the same process, right? The difference is that there is no x in that formulation. I don't know if I need to go through that again, but let me go through the slides that we had last week just to explain this again. Maybe the slides would have made it faster. But if we were to look at the slides from last week, you would see that where I did this, let me see where I did this. Yeah, so this is where I did this, and it will be easy for you to see this here. This is basically the cost function, right? Y minus y hat squared. Okay, so we take the squared down here, and we have 2, right, times yi minus y hat I, right? The y hat is actually mx plus c, so we will do mx plus c, and that gives you, if you do that with respect to m, it has to be with respect to m, because remember, what we are calculating is the partial differential of dj to dm. So that's why we have to use m. So if you do a differential of this piece here, the mxi plus c with respect to m, you are going to get xi plus 0. So that will be times xi. But also remember that there is a negative sign here. So this negative sign is going to make the xi negative. So you're going to end up with minus 2xi, right, into yi minus y hat I. This is how we arrive at that. Now, if you are doing it with respect to c, you basically will do the same thing. So again, del j, del c, right? So again, you take the whole thing, right? And you are going to get 2yi minus yi, y hat I, okay? times the inner one, which is yi minus mx plus c, right? So again, since it's with respect to c, yi doesn't change with c, so it's going to be 0. We'll now look at mx plus c. In the mx plus c, the mx doesn't change with c, so it's going to be 0. So it's only the c that is left. And c is, the derivative of c with respect to c is 1. So it's going to be times 1. But remember, there's still a negative sign here that also affects the c if you open this bracket. So it's actually times minus 1. So you end up with minus 2 times yi minus yi hat. Okay. And again, remember, like I said, the summation, the derivative of a summation is the same as the summation of the derivative of each element. So we will simply just sum the derivatives. We sum all of them across, that's a nice looking sum, but we sum all of them across yeah. So we sum all of them across all of them, and you get that same thing. So this same sum comes in and this same average comes in, and you end up with 1 over n times minus 2. Because the minus 2 that is here is common to all of them, is going to come out. And then you do the summation. I equals to 0, I from 0 to n. And then it will be just yi minus yi hat. That's all. So for C, this is for C. For C, there's no xi element because C is on its own. C is not attached to xi. But for M is attached to xi. That's why there is an xi affecting it. The yi here does not change with respect to the parameters. It's a fixed point that you're trying to predict. So no matter how you twist or adjust the parameters, you know, the value of yi never changes. That's why it doesn't even come in. And that's the way you think about it. As I'm adjusting the parameters, right, the xi is affected by m and so on. So that's the way to look at it. And when you look at it that way, the next screen shows you the value for j and the value for I. The gradient, this is the gradient of j with respect to c, rather not I and j, but m and c. So you get this gradient for dj to m and dj to c. Now I added something. I said if we now have multiple variables and you have y equals m1x1, right, plus m2x2 plus c, right? The c, you will remember the rule. The derivative of this, right, with respect to the m's will still be the derivative of each of them. So when you're doing del m del j del m1, right, you will still just do, it will still be x1 times this. So it's going to be the same thing, except that instead of xi to be x1i, right? Then if you're doing del j del m2, you will now see that it is x2. So it's going to be x2i. That's the difference, right? I'm going to do a better formulation and maybe a better explanation of that when we get to that point. Hopefully I can do that with my Python code, which is much easier to manipulate than the board that we have here. Okay, so let's move on to coding it. I think we've spent a lot of time already, so let's move on to coding it. Right, so this is gradient. We have two gradient functions here. Now there's something I want, okay, so we have a gradient with respect to m and with respect to c. And that's it. Okay, so for us to do the regression now with single variable, we would first of all do it in a loop, okay? And we can just run using a fixed number of epochs, right? An epoch basically is a single iteration of, so this is not a difficult problem, so I'll just use 100. Then you can also specify learning rates. So let me call it alpha. Alpha is a small number. From a previous thing that we have done, if your alpha is 1, it's not going to converge, it's going to blow up. Then we can predict, we can start with initial value of m being 0, initial value of c being 0. So yeah, so we initialize those. So we have our gradient and we initialize that. I would return m and c gradient. So let me return those from my function. Okay. Now the descent, the gradient descent, you can just do a run for, yeah. So you do a run for this number of epochs, okay? So you can just calculate the gradient. So remember, the gradient already calculates the prediction. Really, when you're doing gradient descent, you're really just bothered about the gradient. You're not even bothered about the prediction is part of the gradient calculation. As you can see, a gradient calculation, first of all, calculates a predicted value, right? And subtracts it from the expected or real value. And then we multiply that by x. And then we take the mean and then we multiply by 2. Okay. Then that's for the m. And then for the c, we do the same thing. Predict a value, right? And then you calculate the predicted value, you calculate the difference, and you calculate the mean of the difference, which is the error, mean of error. You multiply by -2. So I get the two gradients, and I simply adjust. This is basically the training of it. And we can plot, we can accumulate the let's accumulate the loss values. Okay, so we can accumulate the loss values. So of course, this means we have to calculate the loss value, which is already part of gradient calculation anyway, but that's okay. Then we can plot it. Yeah. If I run this, then yeah, I need to do this and then run this. So you see our loss graph dropping here. And then you can also plot the final prediction, which is, let's do that here as well. We can plot the original x and y values, and then we can plot the predicted value based on this new, and you get that. Oh, by the way, I need to start this again. So, oh, yeah, I need to have two graphs. So to have two graphs, I need to do plot dot figure 10. Okay. So then we do the first subplot. We don't do the scatter, we only do the losses here. Okay. Matplotlib is another thing that we need to. Yeah, 100. Okay, so we get this another thing. Let me add the color of red to this. We always have to start from so so what I have done basically is plot this. Oh yeah, okay. Yeah, this here. All right. So this is now a plot after it has done the regression training. This was a bit kind of convoluted. So let me again run this in a very simple way. Step one, calculate the prediction. So we already have initialize the parameters. Yes. Step one, initialize the parameters. So we start with m equals to 0, m equals to 0, and c equals to 0. Step two, yeah, epochs and all of this. Then, to train the model, you first of all calculate the error. First of all, you calculate the prediction. So y prediction is, I will not use a function. It's m times x, right, plus c. That's it. To train the model, by the way, you have to use a loop. So for I in range, so you have to do it, a number of times. So for each loop, you calculate the prediction, right? You calculate the error or the loss, which is the actual value of y minus the prediction. Then you calculate the gradient. After the error, you calculate the loss or the cost function. So the cost function, which is the accumulation of the loss or the error. So just to help everyone understand, the cost is the total error across all data points, and we're using mean square error cost function. So we take the error, we square it, right? And we take the mean of the errors. That's the cost function. Then we do the gradient. So for each element, so in this case, it's per element. For each element, the gradient is basically still going to be the same thing, minus 2 times the mean of x, times error. Okay, so we need to do this properly. There are two gradients, a gradient for m, the gradient of j with respect to m. So this is basically dj, dm, right? While the gradient with respect to c is minus 2 times np.mean. In this case, there is no x in there, right? That's the JDC. Then you adjust, right? You adjust the parameter. So the new m will be m, the old m minus the learning rate alpha times the change, right? And then the new c is going to be the old c minus alpha times the gradient with respect to c, right? So this is a much easier way to understand it. I'm doing this to tell you that I took a very complex app. Well, it's not complex. It's just that I put each of them in a method, right? And there's a reason why. But when we remove the methods, instead of calling methods that you'll be asking yourself, but it's really good to also look at it from this approach where, okay, I'm calling a function that does each of these. It's basically the same thing, right? I calculate gradients for each, right? And then I use the gradients to adjust the parameter. It's as simple as that. In this situation, right, same thing. To calculate the gradient, I first of all do a prediction. And this prediction, because it is an entire vector that what we call vectorized, is the whole thing that we are doing. So we are getting for every single data point at a go. Then I do for error, I get the error. Again, each of the y's minus each of the predicted y. So this error is going to match the number of elements here. Then I do for the cost. The cost function is actually a single value now, which is a combination of all the errors. So it's going to give a single value. Then I do the gradient. The gradient is going to be 20 values, one for each data point, right? Because I'm taking the error, which is 20. There are 20 errors. And I'm multiplying it by x. There are also 20 x's, right? And I'm taking the mean of that. So it's each x by each error, right? I get the mean of that. I will multiply the total. The mean is a single value, multiplied by -2. Here, I also have 20 errors here, which I take the mean of those 20 errors and I multiply by -2. So the m and the c are single values. One of them is going to be used to adjust m by multiplying with alpha and subtracting it from the previous m. The second one we use to adjust c. And then we can go plot all the graphs. So the graph plotting is basically the same thing, which I will place here. And we'll get the same thing, right? That is with a single parameter. Now, let's do it with multiple y's. And that's where we can use that Kaggle example. So now, assuming we had multiple independent variables, okay? So in the same way, we will start step 1 by initializing the variables. So instead of just m and c, we are going to have m1, m2, and c. Let's do it that way. So we still started with 0, 0, 0. There are two independent variables. Let's see, in this case, two independent. So because there are two independent variables, there will be also two coefficients. Two coefficients and one intercept. This one intercept is a c. That is always a constant. Well, it's not a constant value in that context, but one intercept. So you see that. Then the rest of the stuff will still initialize. So we'll still initialize alpha, which is the learning rate, and we'll still use 0.01. We'll initialize, I think that's the only thing. We can also epochs, yeah, I forgot that, epochs. So this one we may use more because there's more calculation to be done, more learning to be done. And of course the costs, the losses. Losses of costs. Let me say costs. whatever. It's just an array that contains all the cost functions. Then we now do the same thing. Now, you'll notice that our prediction is now using M1 times X1 plus M2 times X2 plus C. And our error is still the same thing, right? Y minus Y prediction, because there's only one Y, so there will be only one error. Then the cost is going to be NP, is still going to be the mean of the errors for each. So it's the same pattern, right? We still have the same cost. But now we are going to have three gradients, right? So we'll have the M1, which is going to be minus 2. If we're using the same thing, right? It's going to be minus 2 times mean of X1 times error, like I said. So X1 times the error. And then for M2, it's also going to be the mean of X2 times the error. It's still going to be Y minus Y hat. So if you go back to the equation, which I did not put in here, but let me see if I can put this in here. Right, I'd like to put this in here so we can see. It will help with the visualization. Let me see if that works. Yeah, that works. So if you look at this, you are going to see this is the equation for a single variable. So for two variables, I simply will have, instead of just x, right? And now instead of xi, which is x, lots of xi's form the x. The big X is equal to the plenty of the little x's. That's something I did not establish. So let me explain that also here. That whenever you see a big X, and I noticed some people made this mistake. Whenever you see a big X like this, a big X is the same thing as a series of little x's, xi, x1, x2, x3, x4, x5. That's because this big X is a vector. It represents the collection of all the x's. But the x1, x2, or the xi, right, all the way to xn. But xi represents a single value in the vector. So if I have a vector like, and this is very important to know in the context of the notation. If I have an x, which is a numpy dot array, right, and it has three values, 2, 3, 8, 9, 28. I'm just randomly typing numbers, right? This is the big X, and this big X is actually made of 5 small x's. It's the same thing as basically an array of x1, x2, x3, x4, x5, right? Small x's, where the x1, x2, x3, where each of them, let me write it out so it's clear to those who are not Python people, where x1 is 2, right? X2 is what? 3, x3, x3 is 9, x4 is 28, and x5 is 21. So this is the same thing. It's applicable in the mathematical annotation and it's applicable in the programming annotation. So whenever you see an xi, lots of xi make one big X. And lots of yi's make one big Y. And lots of yi pred, yi hat, make one big Y hat. Basically, the little y's, the little letters mean a single data point. But a big one means a collection of all the data points. This is very important. So that mentally, when you are seeing this in code, you don't get confused because we are going to move to a notation like this one, where you are going to see y hat equals big X times theta, big theta. And you'll be wondering, where did we just suddenly jump to? How did we get here, right? The big X is basically all of the small x's in one vector or one matrix, depending on what we are doing. This is very important for me to give you that clarification so that people don't get a bit confused. All right. So when we are now using a vectorized implementation, you're not going to see xi anymore, right? Rather, you're just going to see one big X, and always know that that one big X has a lot of xi's in it, x1, x2, all the way to xn. Now, to solve the problem which we had given, I think I'll just, we need to pull data for x1 and x2. So let me just take some random data. So we already have x and y. So I'm going to take x and y. I'm going to reuse this x, but I'm going to create a new one for x1, right? So this is now x1, which is basically the same thing as x. And then I now have x2. And let me generate that. Give me a second. So I'm going to generate another set of values. Yeah, let me generate another set of values for x1. And I'll put that in here and clean it up. So yeah, this is comma. Well, this looks like it's basically the same data. So let's, oh, okay. Uh, okay. So I am trying to get a different set of numbers because it does look like my numbers here were repeated. So we have so this is a new kind of different set of numbers. Okay, so we have x1 and x2, right? And we still have the same y. And basically that completes the whole loop. So we can now run this. What I would like to do is print. So it's difficult for you to plot a two-dimensional or a three-dimensional graph. There are ways to do that. I think we can look at that separately. So you can see that the only thing I've done here is we now have an extra set of data points of x is independent variables, right? X2. In addition to the X1, which we had before, we've introduced that. And then Y is the same predicted value. But because we have two independent variables, we have to introduce two M's, M1 and M2, and the C, right? We start with zeros. Alpha, epoch, cost, they're all the same. We can tweak the alpha, and the epoch is more because we want to train it more. And then the prediction is now using a formulation of M1x1 plus M2x2 plus C, which I kind of explained at the beginning by telling you that because it is multiple variables, right, each of them will have a coefficient. Then everything else is the same. The error is still the same. Is the true value minus the predicted value is the same. The cost is the same. It's the mean of the square of the error. So you still take the same error we calculate from here. We square this error, right? And then that's for each data point. And then we calculate the mean. Then cost is the same thing. Well, okay, we are appending it to a list so that we can plot it. Then this time around, we will introduce a new gradient. So each parameter will have its own gradient. So you can now see, because we introduced a new parameter here, the M1 in addition to the M2, or the M2 in addition to the M1, which we called M before, we will now have a dm1, which is the gradient for M1. And then we'll have another dm2, which is the gradient for M2. Then we'll have the C, the DC, which is the gradient for C, right? So each of them has its own gradient, right? And the coefficients will have the same formula for gradients because they are basically the same, just replication of the same thing. While the constant or intercept will have a separate gradient function where there is no x in it. The dependency here is that the gradient of M1 depends on x1 times the error. The gradient of M2 depends on x2 times the error. And the gradient of C depends on just the error, right? And then you take the means of each and multiply the means by -2. That gives you the actual value of the gradient. And then after that, the next thing is you need to adjust the parameter. So you adjust M1 by simply multiplying the gradient by alpha and subtracting from it. Okay? And you do the same thing for M2. You take the gradient, the previous value of M2, you multiply it by the gradient, multiply alpha by the gradient, and you subtract that value from M2. C, same thing. So you can see it's the same approach. All we did was we extended the number of parameters. This will still train, this will still converge, and this will still predict. As it is now, we really cannot plot this. We need a three-dimensional scatter because we have two independent variables now, x1 and x2, and then the y, right? So, but there are other ways to visualize that. But I'm not going to go into visualization. I don't want to get caught up in that. The point I want to make is, what if I wanted three independent variables? I have three independent variables here. So let me just basically copy x2 and call it x3. So yeah, it's the same value, but it could be different, right? In this situation, I would introduce a third coefficient, right? The others remain the same. Everything else is the same. The prediction now includes that third coefficient. So it will now be M3 times X3. Okay? And then yeah. So the other thing is everything else is the same, error and all. We now introduce a third gradient for the M3. Same formula as the other two coefficients. Okay? And then That's it, right? The update part, the update function, still the same thing. Introduce another one. And that's it. So you can see how the multiple variable becomes easy. It's a generalization of the single variable. It is still going to converge. It converges. And it is able to predict. It will be able to predict as well. So effectively, well, I'm getting nans here. I don't know why I'm getting nans. Probably the it's blowing up actually. It's blowing it's almost impossible. If you actually were to check, yeah, we're actually getting values blowing up. That's because these numbers are very large. So typically you will do what we call a normalization. And this is very important when you are now doing gradient descent with multiple variables that can become very big. You can look at these numbers here. The numbers are huge, right? In order to give us an idea of what these numbers look like, I am going to slow down the process and actually go through each epoch one by one, right? I'm going to start off, and instead of running it, instead of doing this loop, right? I'm going to take this loop out to a separate code block, and I'm going to run it one step at a time. So let's start with this. Okay, so this is a code block that runs a loop, and then this is the code block that prints and plots. So the code block that runs the loop, I'm going to do something. I'm going to print each parameter when we run each iteration. And I'm going to run it manually instead of the epochs that we have here. I hope we are still hearing me. Okay. So yes, you are going to get a lot of nans because you have to normalize, and this is a very important thing. That's why I have to show it. So let's just print this. The numbers are huge, right? In fact, in addition to printing the m's, I want to also print the gradients. When the gradients become really large, your values can become really large as well. Of course, that's why you adjust the learning rate. Well, one thing you could do is adjust the learning rate, make the learning rate really small. Another thing you could do is normalize. If you're getting nans, it's probably because the numbers are so huge. So let's look at a few things that you could do in this situation. But for us to know what to do, we need to kind of understand the problem. And that's why it is good to do all of these things manually. So let's start off by printing the gradient, right? So we print the parameters. So then we print the gradients. So print the tm1, TM2, TM3, and TC. Right, so let's just look at all of that. So we'll start again. We will initialize our x1, x2, x3 arrays and our y. Okay, then we now run a single iteration. So let me just make a comment. This is the part where we iterate multiple times to train, to adjust the parameters and train the model. So here I run the first iteration. So you can already see we have gradients that are pretty high. Minus 260, minus 649, minus 649, minus 38. Those are the 4 gradients. The parameters themselves are small. So you can see parameters started small. We'll have this really huge gradient. Okay. If I run it again, of course, the parameters will jump up already, and the gradients are even larger. So remember what we said about the cost function curve. If your gradient is too large, or if your gradient times alpha is too large, you will not converge. It's already going very negative in the opposite direction. The gradients are very large, right? So we're making big jumps. And when we make big jumps like this, right, the tendency is that you will hit nans, what we call explosion of gradients. This is basically what we call explosion of gradients. The gradients are getting really big, right? If we run this again, you can now see, look at the magnitude. Don't worry about the sign, right? The magnitude, this is now 52,904. Your gradients are getting bigger and bigger. So that means it's climbing up the gradient. It's not going down, because it's jumping around with really big, and you can see your parameters are increasing. If you run this for a number of epochs, it's not going to converge. Rather, your parameters will just keep blowing up, and your gradients will keep blowing up even more and more, right? This happened the first time. When this happens, what you have to do is 2 things. One thing is you can normalize, right? But for a simple linear regression problem, you simply reduce the learning rate. You can reduce the learning rate until this thing converges, right? So you can see it's blowing up. After a few epochs, it's going to go out of the range of the numeric range of Python. That's where you get the nans. Nan basically means you have exceeded the numeric range. So you can see I'm getting to 10 raised to the power plus 34, 10 raised to the power plus 35, on the parameters, and the gradients are blowing up. The higher the parameters, you are basically climbing up the gradient, not going down. That's because your learning rate is too high. So what do we do in this case? We reduce the learning rate. We can reduce it by, you can see it's blowing up to power of 64. E raised to power E64. E plus 64 means 10 times 10 raised to power 64. So think of it as a number 2 with 64 zeros after it, right? It's blowing up. At some point, it is going to exceed the limit of, Python, or Python floating point numbers, which I can't remember what that limit is. But once it exceeds that limit, you start getting nans. If I want the first of these parameters exceeds that limit, you get nans. So that's why we got nans there, because of course we're running it, 500 epochs is what we're running. We'll definitely hit nans. So how do you solve this? You bring your learning rate down. So I'll now take it down by a factor of 10 to 0.001, and I'll rerun this whole thing. And then we'll see if it is going to converge. You are still getting large gradients. The gradients will be the same. They're still the same size, because we are still at the same point on the curve. We're still on the same. Well, 500 epochs is good for, linear regression. You need a lot of epochs for training more complex models. But this is a very simple model with just 2 parameters or 3 parameters. So 500 epochs is actually too much, right? But anyway, so if you look at this, the gradient is the same, but we've lowered the learning rate a lot. So if I were to even print this as, updates. Let's call it updates. So the gradient is there, right? The updates is what you actually apply, which is minus alpha, right? Minus alpha times dm1, okay? Minus alpha times dm2 minus alpha times dm3 and minus alpha times c. So this is, yeah, these are the updates. So that's the actual value that will be applied, okay? So when you do this, you can see the updates are much less now, right? With a slower learning rate, and the parameters are changing slowly. They're not jumping. So this one will converge. In fact, if I may, I could even include the loss. We can include the, where's the loss? The costs. So yeah, the cost for this iteration. Or I could just print all the costs. Let's print all the costs, which is all the costs for all the iterations. So you will see, well, okay, this will be difficult to see. So let me just print the cost for the current iteration, 38.9. So it kind of goes down. You can see it's going down. You can now see your gradients are not blowing up. Your gradients are coming down. Your cost is coming down. That is why the learning rate is called a hyperparameter. You have to tune it, and you have to know how you are tuning it, because if you are not tuning it properly, your model will not learn. It will basically just blow up due to exploding gradients. There's also the opposite of exploding gradients, which we call the diminishing gradients, when the gradients get so small and it's not learning. So this is the reason why we blew up. And if we continue to run this, right, I can still, run this based on the number of epochs, right? You now see that we will have, you now have a cost function of a cost of 2.8, right? After 500 epochs. And we can come down here and print everything. And you can see this has also converged. So that's one way. I don't want to talk about normalization yet, but that's a way to do it. I think we will discuss normalization when we are talking neural networks, where there are so many parameters, you can't just change learning rates anyhow. So there are other ways that you can manage exploding and diminishing gradients. Normalization is one of them, right? But we'll talk about separately. So for those of you, if you're having NANs, for this kind of simple problem, the easiest thing to do is just reduce your learning rate. Reduce it by a factor of 10. If you still have NANs, reduce it by another factor of 10. And you keep doing that. And at some point, the updates will be so small here, because the learning rate determines the update. The gradient might blow up and be huge, right? But the updates will be very small, because the update is affected by the gradient. So that is linear regression of multiple variables, multiple independent variables. Now, there are other kinds of regression. There is polynomial regression. There is logistic regression. As a matter of fact, I had wanted to go into logistic and polynomial today, but we ran out of time. So this week, we're also supposed to go into the more advanced, the other methods using, decision trees, random forests, using support vector machines and so many other things. But we may have to slow down this week, right? So that everybody catches up. So next week, we will do those from next week. That will shift our timing by 1 week. But I hope, this will help a lot of people. So on Wednesday, we will continue with linear regression with linear regression using polynomial. Sorry, not if. So that's polynomial regression basically. So we're going to do polynomial regression, and then we are going to do logistic regression. Now, before I end this, I'm going to now transform this because I've seen a question here. What if the independent variables were 900 M's, so 900 features? So that is where you will bring in the matrix vectorization. So let me see if I can express that. I think it's easier for me to do this with code than with mathematical equations. So, but let's bring in a mathematical equation. So remember, we started this off with this. This is a series of, this is basically one linear equation, multiple independent variables, right? Now, there is a way you can rewrite this, okay? So in order not to waste a lot of time, let's take this one that we have here. And we're going to rewrite it as matrix, which is what a lot of people did not understand this, especially when we were taught matrices, right? That you can actually take so you can actually take this equation, y, right, which is y equals beta, let's call it b0 plus b1 times x1, right, plus b2 times x2 plus b3 times x3. And we just keep doing that, all the way to bn times xn. Okay? Now, there are two ways you can write this. You can also write this, if I may do an annotation here, you can also write this as a summation, which is what you will see when we start doing neural networks. You will actually see this, right? Where we will write this and we will use this form. Well, we'll write it as y equals b0 or beta 0, which in neural networks we call this a bias, plus a summation, right, of from I starting from 1. So let's start from 1 because I actually starts from 1, b1, x1, b2, x2, to I stopping at n, right, of beta I times xi, right? That is a summation term. Then, of course, the epsilon. Now, so we have that form, and it's an interesting form. So I'm going to actually I'm going to grab this form, and I'm going to grab this form, and I'm going to stick it back in here. So it will be here, right? So we would have this form of okay, so we have that form while I clear the annotation. So yes, so you can now see that we have rewritten this into a shorter, more compact form. If I look at this, it is also y equals b0, okay, plus we could do np.sum, right, bi, but that's not really how we write it in programming. In programming, it's not yet, we write it out as a matrix. So when you're writing this out as a matrix, there is a way we handle matrices, right? If you look at this, if for those of us who remember the matrix multiplication, if you're multiplying a vector in matrices, you will have this, right? And then you will have this, okay? So you have a matrix that is, or a vector that is n by 1. it has n rows and one column, and then it has one row and n columns. So inside this, inside this vector, which is basically a 1 by n matrix, and inside here, so the interesting thing is that you can pull it out anyhow you wish, right? You could pull out the constants or the coefficients, the betas here. This is B1. Leave B0 for now, B2, right? B3, B4, beta 4, and so on. And then you have here X1, X2, X3, and so on. So if you do that matrix multiplication, you will find that it is giving you back exactly this formulation that we have here. It's giving you back exactly this formulation, right? So if it's giving you back that formulation, what it means effectively is that I can now write Y as a matrix or a vector, what we call a dot product, right? It's a vector product or a dot product. So that dot product will be Y equals beta. Now it's a big beta, right? Dot X, right? Where you can now say beta is a matrix. So in this case, we represent the matrix or the vector by a simple ND array that contains the coefficients. So you have B1, B2, B3, B4, B5, and so on, all the way to Bn, right? And then X is also another vector that matches the same length as B. So remember, the X is transpose. It is X, small x's. Remember, I told you the big X is made up of lots of little x's, right? So, and so on, all the way to xn, right? So you can now do a matrix dot product, which is what I just did here. So you would do NP dot, right? You do a dot product, and then you put the beta, and then you put the X. That's a dot product. So just to prove this, okay, let's assume these actually are not valid equation, valid programming, code. So we'll have mistakes there. But let's start with beta. So for your information, in machine learning, the coefficients we use theta, not beta. We use theta. I don't know how I can bring out the theta, but yeah, I think there's a way I could get theta out, right? But I've not figured that out yet. So, so we have, yeah. So I found the theta. But that won't show up here, right? Because this is not. But on our text block, it shows up, right? Hopefully. Okay, didn't really show up. That's a mathematical pattern. So so you have theta, right? Which represents the parameters. Okay, let's just call it theta. This is basically a vector of the parameters. So there are two ways we can represent this, right? So one way is it's going to be a list. So instead of having to do each parameter, separately, right? We can now have theta as its own vector. So let's assume I had 10 x's, right? 10 big x's, okay? sorry, not 10 big x's, 10 little x's. So a single data point that has 10 little x's. So each theta would contain 10 values. So let's just take some random values. Okay, let's just go with how many? 1, 2, 3, 4, 5, 6. Right. So this is now a vector of the coefficients. This vector of coefficients is the parameter list. It's a parameter, basically. So if we want to convert it to NumPy, we simply just do np.n.array, right? And we have it. The same way, x. Now, the interesting thing is that remember that x is made up of lots of data points. Each data point of x is a single entry in this array. So this is one data point for x. So for a single data point, you have x1, one little x1, one little x2, one little x3, and one y. But for us to have all of these x and x's, we now have lots of little x's, forming the x1, the big x1. But we also have 3 of the big x's. So we have the x1, x2, x3. So you will then find that you now have a big brother, big X, right? That is going to be made up of an X1, a big X1, a big X2, a big X3, a big X4, a big X5, a big X6, a big X7. There has to be 7 of them because remember we're having 7 independent variables. Each of these X is an independent variable. And each of these x has 20 small x's in it. So each of those 20 small x's is a data point. So you will now represent this from the standpoint of representing as a matrix. The big X is actually a 20 by 7 matrix, right? So let me sketch that so we can see. The big X is actually a 20 by 7 matrix. So I'm just going to generate random numbers here because it's, or maybe I ask an LLM to do it for me so I don't waste too much time. So, but that is the idea, right? I'm going to walk through it. Yeah. So I'm going to ask ChatGPT to generate for me a 20 by 20 row by 7 column matrix with random values and print in the format. So I'll tell you the format range. Okay. So while doing that, what I just want to explain is that when we now have multiple, yeah, this is nice. So when we now have multiple of such, right, it is really good that we visualize all of this, okay? So I have asked ChatGPT and it has generated it for me, and I'm going to put that in here in a text block. I'm going to put it in, this in this form. Okay. So we can all see. So this is now what it looks like. So I can further edit this so that it is easy for everyone to see that this is X1, for example. Okay. By the way, if you want to know how I can modify multiple rows at once, everybody that knows VS Code should know this, but if you don't know how to do this, then you don't know VS Code. You're not a power user. Okay, so let me add in some zeros here. And then I can basically just copy this and paste it. Okay, I missed 10. Okay, so what do I do? I will still copy this and paste it here. And then we come up here and put in the 10. And then we put 20. So we get this nice looking thing where you now see that each row is a single data point. Each row is a single data point. Then each column is a feature. Basically, each column maps to one of the independent variables. So we can also add that in here and say that this column, for example, is M1, right? It maps to coefficients that is M1. Whatever name we want to give to it, right? It maps to that coefficient. Let me also, for the sake of, balancing things out, let me call it M01. So you can see that corresponds to 7 features, right? And that's really what it is. So when you hear of rows and columns, right? Okay, I was expecting 7, but it gave me 6. I wonder how that happened. So one of the things you learn is LLMs don't know how to count. I actually told it to give me 20 by 7, but it gave me 20 by 6. That's weird. Okay, 1, 2, 3, 4, 5. Okay, that's correct. So I think I made a mistake. All right, so we can also decide to put line in between. So basically, what I'm saying here is that this is a true visualization. In your mind, this is the picture you should have in your mind when you are, trying to train. You can now see the amount of data. This is data you have, right? You have the X. So when we're doing linear regression with a single variable, we had only one M, right? And then for that M, we had lots of X's. So for your information, this should be little x's, not big X's. So let me correct that. Even though you could also look at, yeah, this should be little x's, not big x's. So this X01 corresponds to this. So for this entire column, right, the data for this entire column, all the rows forms the big X. So in a way, you have to differentiate between data points and features. That's one of the things that you always need to remember. So the convention is always different. You have a subscript I for the for each X or for each M, right? For each feature. Then you have a superscript I in bracket, which is sometimes used for the different data points or batches. So they can be all of that. So when you add, you now have this entire big array is this big X you have here, which is basically all of the each of the features put together, right? So when you see a big X like this, you know that it's a matrix. And that's why you will now see things like an N and M by N matrix. So in machine learning, the M usually is used to represent the number of features, right, or columns, or independent variables. These all map to the same thing, right? While N is the number of data points or samples or batches or batches, yeah, batch size, right? So you always see that M by N. So M is going to determine um, the number of coefficients, basically, while N is going to use that to determine the number of data points, basically. So that's it. So I hope that helps to answer that question of if we had lots of. So the formulation now is going to be what I have here. So let me put this up. The formulation now is going to be y equals x theta. So the y hat is the prediction. X is that big X I talked about, where you can see it's the M by N matrix of features, right? Where the M is the number of features and the N is the number of data points or the number of samples. So Y is going to be a vector of should actually be a vector of size N, right? Which matches the number of data points, because for each data point you make a different prediction. So Y is going to be the number of data points. Then theta is going to be the number of features, right? Which should be M plus 1. But I think there is a mix-up here. I think here, okay, this is a premise. We have M training examples. I used N for that, but here this is M that is used for training examples, and N is the features, right? So if you have that, then you have M by N. The training examples is always taken first. That in the A by B or C by D or whatever, the number of data points is always the first. And the number of features is always the second. And then the Y, which is the labeled value or the expected value or the true value, will be the same as the number, as the number of training examples or number of data points or number of samples, right? While the N is going to be the number of features, which corresponds to the number of coefficients, right? Which corresponds also to number of columns. And then typically, what we do is to also take care of the C, which we have understood to be a constant, an intercept. We introduce the value of 1. So let me explain that. So here, back in this, we didn't put in the C, but the C cannot be thrown away. So the C, well, we can put it either at the beginning or the end. It doesn't really matter. But let's see, where do I want to put this? Let me put this at the beginning, right? So for neural networks, this also is called We also call it bias. So yeah, it always has a value of 1. It always has a coefficient of 1, right? So the value of, in order to make this work, we will put it here, right? And yeah, so this is now C. It's basically just C or M00. So that's another thing. We can just call it M00. That is M0 or beta 0, right? I'm just using, I'm prepending these things. So maybe I shouldn't. So let's call this M0, M1, M2, M3, M4, which could be any alphabets because we're using M's before, right? And M7. Okay. Now, so M0, which we were calling C before, right? This will always have a coefficient of 1 because you don't multiply anything by it, right? There's no x multiplied by it. So we simplify the whole deal by just saying the value is 1. And that's it. We added third zeros just so we can get the balance, right? And that's M. So you can now see that M0, which is a C, if you take this system of this matrix and you do the necessary maths, you are going to, if you do this multiplication, you're going to get M0 times 13.15 M1 times 10.90 M2 times 5.03 M3 and so on. So these are coefficients, right? This is a coefficient of the constant of the intercept, which is always 1. In other words, it is not x, is not dependent on x. It's always c times 1, which is c. It's always c. So that's where this comes in, and that is how you can understand this formulation here. That says basically that at the end of the day, y equals x0, where you have an extra thing. And then with that, you can have this formulation for the cost function, which is x theta plus y minus y. Remember, x theta is now, theta is m, basically. Theta is all of the m's, all of the coefficients. So mx is the same thing as x theta, but the reversal is to allow for that transposition. It's actually a transposition going on. Remember, dot product. So basically the same thing as mx plus c. The plus c, the c has been subsumed into the theta as I just showed you. So it is now x theta minus y. Y is the expected value or the true value or the you know the y in the data point. Then you have this thing here, which is what we call an L2 norm. L2 norm, absolute value. Then you square it, right? Divide it by 1/2m. This is now the cost function, mean square error. You may ask, why is it 1/2? That's an interesting question. But 1/m at least is understood because you are dividing this 1/m. This m, remember, is the number of training samples. So it's the same thing as divided by n. The reason why we have to do 1/2 is because when we eventually do the gradient, we want this 2 that will come out from here to cancel out so that we'll have a very simple, straightforward gradient function. So the 1/2 was brought in just as a constant to help that. It's not like the 1/2 really has anything more than that. And that's it. This is just another way of writing it. Instead of saying f of x, you have h theta of xi. I will explain this more, this notation, in case you see it. But at the end of the day, it is what we call a vectorized version of the linear equation. This is the vectorized version. And how you solve it is by calculating the inverse of the x and multiplying it by, this is the inverse of the x multiplied by the y. and you get the theta. So I'm not going to go through all of this, right? Because we've already gone through it programmatically. This is now the mathematics of it, and it might be a bit difficult, but at least I think I have explained um, it with code. Cost function is basically the same thing as the gradient. Again, the mathematics makes it look really challenging, but it's the same thing, right? You have the cost function here, you have the gradient, right? And then you do the gradient descent, what we call batch gradient descent. We'll talk about that a bit more. I'm going to bring this back up when we're doing neural networks. So let's not get too hung up on this. We have level 2, L2 regularization and all of that. So it's still the same process, right? But this time around, instead of us taking each individual feature one by one, each individual coefficient, we are coming up with a generic form that we can use to do any number of coefficients, and that is it. So I want to end here. I think we've gone really far. On Wednesday, we're going to look at logistic regression. Then we'll also look at polynomial regression. I'm going to try to not go into all of the maths anymore. Just show you how you can do this very simply with sklearn. We will start that from Wednesday. We'll do a little bit of looking under the hood, but after that, this is hopefully this will be the most dramatic part of this machine learning course when it comes to maths. We will have a bit of it again when we get to neural networks, but after that you just call functions and that's it. So I'll end it at this point. Thank you very much. I'm going to end the recording.